This video is about matrix representations of linear transformations. We're going to define the matrix representation of a linear transformation. Then we're going to do some examples where we find those matrices. Then we're going to define eigenvalues and eigenvectors of linear transformations. And then we'll do some examples where we find a diagonal matrix representation of a linear transformation. Instead of starting with the definition, we're going to develop the idea of a matrix representing a linear transformation. So let's say we've got a linear transformation T that maps from U to V. U and V are arbitrary vector spaces. V is a basis for U is a vector in U, C is a basis for V, and T of U is a vector in V. We can picture that like this. Here's the vector space U, here's the vector space V, here's the basis B for U, here's the basis C for V. Here's the vector U in U, which is mapped to T of U over here in V. We'll say that U is n-dimensional and V is m-dimensional. Then what we're going to do is introduce Cn and Cm. We know from the notes on isomorphism that if U is n-dimensional, it's isomorphic to Cn, and V, being m-dimensional, is isomorphic to Cm. Also, given the basis B, we can write the coordinate vector of U relative to the basis B, and that coordinate vector is going to be in Cn. In fact, we can think of that coordinatization as a linear transformation itself. So I can map U down here into Cn. So here's the coordinate vector of U relative to the basis B. And I can do the same thing for T of U. Using the basis C, I can write the coordinate vector of T of U relative to the basis C, and that vector is going to be down here in Cm. So here's the coordinate vector of T of U relative to the basis C. We can label this transformation rho sub B, and this one rho sub C. These are the coordinate transformations relative to the bases B and C, respectively. And now, if we can connect the coordinate vector of U relative to B by some transformation from Cn to Cm over to the coordinate vector of T of U relative to C, then we would have a connection from U down to this coordinate vector over to this one, back up to T of U, which we could use to get from U to T of U instead of going through T itself. So I've labeled that transformation M here because in fact M would be an M by N matrix. Any linear transformation from Cn to Cm has a corresponding M by N matrix that implements the transformation. So now we want to consider, is there such a matrix M? Is there a linear transformation from this vector to this vector? And if so, what is it? Before we do that though, let's think about why would we want to do that. So I've labeled U and V above this red line as the world, and I've labeled Cn and Cm below the red line as, quote, inside a computer. In practice, we often have an arbitrary vector space U and some linear transformation to another vector space V. V could be the same as U, but it doesn't have to be. And we want to implement this transformation, quote unquote, in the world, meaning this transformation would be implemented by some physical system. It could be an electrical circuit, a mechanical system, a biological system, etc. And in particular, we want to be able to compute the images of U under T. So for example, if I consider U to be the input to the system represented by T, T of U would be the output, and I want to be able to compute the output T of U from U, and I want to be able to do it easily and quickly. Well, quick, easy computations are what computers literally are designed for. To perform T in the real world might be computationally very intensive. For example, let's say U is an audio signal. Say it's your voice in your cell phone. And T is a noise reduction algorithm that's going to reduce the background noise and enhance the quality of the signal. And T of U is the output that your friend is going to hear on their phone. So U is you saying, hey, what's up? T of U is your friend hearing your voice saying, hey, what's up, in a way that's cleaned up and the noise is reduced so it's more intelligible. Well, in that case, U is in the vector space of audio signals. T of U is also in the vector space of audio signals. And T could be a pretty complicated algorithm implemented, for example, by an electronic circuit. Instead of going from U to T of U directly, though, what we're going to do is go from U into the computer using a basis. If U is the vector space of audio signals, B would be, for example, a basis of complex exponentials. But remember, when we coordinatize U, it's now a vector in Cn. So it's just an array of numbers inside the computer. And then M is just a matrix. So computers are really good at multiplying matrices times vectors. So if I multiply this vector by this matrix to get this vector, well, rho sub c is an invertible transformation. So I can use it to get back up to t of u. I just take the entries of this coordinate vector, multiply them by the basis vectors c and add them together, and there's t of u. Now, it looks like a roundabout way to get there in this picture, but many times in practice we can go down and over and up in real time much faster than we can go straight across from u to t of u. In any case, this is an example of why we may want to do this, why we may want to represent a linear transformation with a matrix. Okay, to see how this works, the first thing we're going to do is represent u as a linear combination of the basis vectors b. So these betas are going to be the entries of the coordinate vector for u relative to b. And then t of u is just t of this thing. And now what we're going to do is use the linearity of t to figure out what is the coordinate vector of t of u relative to c. Well, I just replaced t of u with this expression here, which I've expanded here just so it's easier to look at. And then from here down to here, I'm just using the linearity of t. Here are the individual steps. Essentially, I've got t of a linear combination, so the image of a linear combination of basis vectors. And down here, I have a linear combination of images. So the linearity of t says the image of a linear combination is a linear combination of images. And we can write that in the compact sigma notation like this. And the next thing we'll do is write this vector equation as a matrix equation. So on the left side, we have the coordinate vector of t of u relative to c. On the right side, we have this linear combination of coordinate vectors of t of b sub I relative to c. Remember, b sub I are the basis vectors for the basis b of u. Writing that vector equation as a matrix equation, we can take these vectors, put them into a matrix as the columns of the matrix, take these coefficients, put them into a vector as the entries in the vector, and now we have a matrix equation. Furthermore, this vector is the coordinate vector of u relative to the basis b. Remember back here we wrote u as a linear combination of the basis vectors b1 up to bn with the betas as the coefficients. So there's the coordinate vector of u relative to b, which we can now identify down here. So we can replace this vector with the coordinate vector of u relative to b. So I've got on the left side the coordinate vector of t of u relative to c is equal to some matrix times the coordinate vector of u relative to b, and that's just what we were looking for. So we'll call this matrix M, and in particular we'll call it M with a superscript t and a subscript b, comma, c. So it's kind of a complicated notation, but there's a lot of information here. This matrix is called the matrix representation for t relative to the bases b and c. And the columns of the matrix are the images of the basis vectors b, and then we take the coordinate vectors of those. So this is the coordinate vector relative to the basis c of t of b1. The second column is the coordinate vector relative to c of t of b2, etc., up to the coordinate vector relative to c of t of bn. And that gives us the equation that we want. The coordinate vector of t of u relative to c is equal to this matrix M times the coordinate vector of u relative to b. So if we come back to our diagram here, yes, there is in fact a matrix M that I can multiply by this coordinate vector to get this one. And that matrix is this matrix for t relative to b and c. Okay, all of that leads to the following definition and theorem. We're just going to define the matrix representation of the linear transformation to be this matrix that we just found. So if t maps from u to v, b is a basis for u, c is a basis for v, then this matrix, whose columns are the coordinate vectors relative to c of the images of the b basis vectors under t, that's called the matrix representation of t relative to the bases b and c. And then the work that we just did is essentially the outline of the proof of theorem 1.1 here, that says if t is a linear transformation from u to v, and b is a basis for u, and c is a basis for v, then this equation holds. In other words, this matrix that we just defined up here, I can multiply by the coordinate vector of u relative to b, and that will give me the coordinate vector of t of u relative to c. Okay, let's see how that works with an example. Let's say t maps from p2 to p4, and it's given by this equation. T of p, where p is a vector, it's a polynomial in p2, so it's a second degree polynomial. T of p is equal to p plus 2x squared times p. and we'll let B and C be the standard bases for P2 and P4, respectively. And what we want to do is find the matrix representation of T relative to the bases B and C. In other words, we want to find this thing. Okay, well, remember the standard basis for P2 is 1x and x squared. Likewise, the standard basis for P4 is here, and here's our definition for the matrix we're looking for. So we'll just work from the inside out. We're going to identify B1, B2, and B3. In this case, we have 3 B basis vectors, so we go up to B3. So we'll call B1, 1, B2, x, and B3, x squared. And then we're going to compute the images of each of these one by one under T using the function rule here. So T of B1, well, that's going to be replacing the P with a B1 plus 2x squared times B1. Well, B1 is 1, so I get 1 plus 2x squared times 1, or 1 plus 2x squared. So this is a polynomial in P4, even though it's only second degree. Remember, P4 is the set of all polynomials of degree less than or equal to 4. So a second degree polynomial is in P4. Similarly, T of B2 is here. Well, B2 is x, so I get x plus 2x squared times x, or x plus 2x cubed. B3 is x squared, so I get x squared plus 2x squared times x squared, which is x squared plus 2x to the fourth. So here's the image of B1, the image of B2, and the image of B3. Next, I want the coordinate vectors of these images relative to the basis C. Well, since C is the standard basis, we can just find these by observation. In other words, T of B1 is equal to some linear combination of the C basis vectors. So we could label the C's like this. C1 is 1, C2 is x squared, x cubed, C5 is x to the fourth. Remember, since we're starting with 1, we go 1, x squared, x cubed, x to the fourth. When we get up to x to the fourth, we actually have 5 basis vectors. So each of those C's is going to be multiplied by a scalar, which I've called gamma here. So gamma 1 C1 up to gamma 5 C5. I'll replace T of B1 with the polynomial we found, 1 plus 2x squared up here. And then on the right side, I'll replace the C's with the polynomials up here. And then I can write 1 plus 2x squared with some 0 terms here to write it out as a fourth degree polynomial. So there's no x term here or x cubed or x to the fourth, but I can put them in with a 0 coefficient. So 1 plus 0x plus 2x squared, etc., equal to this linear combination. And I can just observe, well, 1 has to be equal to gamma 1, 0x has to be equal to gamma 2x, 2x squared has to be equal to gamma 3x squared, etc. So I can essentially read the gammas right off of this linear combination, 1, 0, 2, 0, 0. And there is my coordinate vector of T of B1 relative to C. We can do the same thing for T of B2 and T of B3. T of B2 was x plus 2x cubed. Well, if I write it as 0 plus 1x plus 0x squared plus 2x cubed plus 0x to the fourth, I can just read the coordinate vector right off the polynomial, 0, 1, 0, 2, 0 here. And likewise for T of B3, 0, 0, 1, 0, 2. Putting it all together, I put those 3 vectors as the columns of a matrix, and here's the matrix for T relative to the bases B and C. So we found the matrix representation of T, and then we want to use it to calculate T of 1 plus x. Well, how would we do that? Well, this would be like T of U in the general description that we talked about. To find T of 1 plus x, we're going to find the coordinate vector of 1 plus x relative to B, multiply that by the matrix that we just found to get the coordinate vector of T of 1 plus x relative to C, and then use the inverse transformation from C5, where the coordinate vector of this is, back to P4, where this vector is, and that will give us T of 1 plus x. All right, so we start by writing 1 plus x as 1 plus 1x plus 0x squared, and we can just observe 1, 1, 0. There's the coordinate vector of P relative to the basis B. Then we multiply that vector by the matrix for T relative to B and C here to get this vector. Notice this is in C5, and this vector is the coordinate vector of T of P relative to C. We're almost there, so now we take this vector through the inverse transformation back to P4 to figure out what T of 1 plus x is. So we're going to use the entries of this coordinate vector as the coefficients of the basis vectors for C. So it's going to be 1c1 plus 1c2 plus 2c3, etc. And then we'll replace the c's with the actual vectors in P4, 1, x, etc. And then just simplify, and we get 1 plus x plus 2x squared plus 2x cubed. And there is T of P, which in this case is 1 plus x. Now we can check this by using the function rule directly. T of 1 plus x is 1 plus x plus 2x squared times 1 plus x. We distribute the 2x squared in here, we get 2x squared plus 2x cubed, and there it is, the same thing that we got up here. Now in this case, it's a lot quicker to just do this. We could have done this from the very beginning. We didn't need to find the matrix representation for t, let alone the coordinate vector of p relative to b and t of p, etc. This would have been a lot quicker. But this is a simple example that illustrates the idea. Like I said, there are lots of practical examples where this computation would be much more difficult actually than doing all of this stuff, especially since this stuff is done inside a computer. Okay, next we want to talk about eigenvectors and eigenvalues of linear transformations. But before we do, we have a few things that we need to define. We're going to consider the identity transformation on V. So we saw this transformation before in the video on linear transformations. I sub V maps from V to V, and it just maps every vector in V back to itself. Well, what would the matrix representation of I relative to two different bases B and C look like? Well, it would be the coordinate vector relative to C of I of B1 and then I of B2, etc. Well, I of B1 is just B1 because I maps every vector like B1 back to itself. So I just have the coordinate vector of B1 relative to the basis C, the coordinate vector of B2 relative to C, etc. And then we're going to call that thing the change of basis matrix. Since the transformation isn't doing anything to the vectors, the only thing that's changing is the basis. We're going from one basis to another. And we can see that here in the change of basis theorem. So if V is a vector in a vector space V with bases B and C, then the coordinate vector of V relative to C can be computed from the coordinate vector of V relative to B simply by multiplying by this change of coordinates matrix. We can picture that down here. Here's V and V. The identity transformation maps V to V. So the whole point here is not the transformation, it's changing from this basis representation to this one. I've got V and a basis B here, and this is the coordinate vector of V relative to that basis B. And I want to change that over to this coordinate vector relative to a different basis C. And this matrix, the change of basis matrix, will do it. All I have to do is take this vector, multiply it by this matrix, and I get this vector, as we can see up here. If you've taken Calc 2 or Calc 3, then you've seen different kinds of coordinate systems, like polar coordinates or spherical coordinates, cylindrical coordinates, etc. Why do we change coordinate systems? To make things easier. If I want to describe a circle, polar coordinates is much easier than rectangular coordinates. Likewise, if I want to describe something spherical, spherical coordinates are a much better coordinate system to use, better in the sense that the computations will be a lot easier. That happens in lots of applications as well. I might have a vector space with a certain basis B, and I have the vectors represented as linear combinations of the B basis vectors, but what I'd really like is to have them as linear combinations of some other basis that makes computations simpler. Well, I can use this change of basis matrix to just change bases inside a computer. This theorem tells us that the change of basis matrix is invertible, and that's a direct result of the isomorphism from V to Cn. We use this notation to mean the inverse of the change of basis matrix from B to C, and that is actually equal to the change of basis matrix from C to B. We can see that if we come back here, B and C were chosen arbitrarily. If I just exchange B and C here, I can see that the coordinate vector of V relative to B is equal to the change of basis matrix from C to B times the coordinate vector of V relative to C, which would take me back in this direction. So if I have the coordinate vector of V relative to C, this matrix, the change of coordinates matrix from C to B, will get me this coordinate vector of V relative to B. Well, if this matrix is invertible, then its inverse must be equal to this matrix that gets me back from here to here. If this matrix takes me from this vector to this one, the inverse has to take me from this vector back to this one. So that's essentially an outline of the proof of this theorem. This next theorem, similarity and change of basis, will be the foundation of the examples that we'll do next. If T maps from V to V, and B and C are two different bases, then the matrix for T relative to B and B is similar to the matrix for T relative to C and C, and these change of basis matrices are the matrices that produce the similarity. Now we can finally define eigenvalues and eigenvectors of linear transformations and get to some examples. Recall from the eigenvalues and eigenvectors notes and corresponding video, every square matrix has eigenvalues and corresponding eigenvectors. Now that we've seen that there's a matrix associated with every linear transformation, it shouldn't be a big surprise to see that we're going to talk about eigenvalues and eigenvectors of linear transformations themselves. We'll say if t maps from v to v, it's a linear transformation, then a non-zero vector v in v is an eigenvector of t associated with the eigenvalue lambda if this equation is satisfied. T of v is equal to lambda times v. Remember, for a matrix A, v is an eigenvector associated with the eigenvalue lambda if this equation is satisfied. A times v is equal to lambda times v. So we can see how similar this equation is to this one. This next theorem tells us the relationship between eigenvalues and eigenvectors of a transformation and eigenvalues and eigenvectors of a matrix. If t maps from v to v, it's a linear transformation, and b is a basis for v, then little v is an eigenvector of t corresponding to the eigenvalue lambda if and only if the coordinate vector of v relative to b is an eigenvector of the matrix for t relative to b and b corresponding to the eigenvalue lambda. We can picture that over here. I've got v up here, t maps from v to v, so here's little v and t of v. The bases are the same in this case, so this is not c, it's b in both cases. Here's the coordinate vector of v relative to b in Cn. Here's the coordinate vector of t of v relative to b, also in Cn. And here's the matrix for t relative to b and b, since the bases are both b in this case. We're not changing bases, we're changing from v to t of v. And we're using the same bases. That's why this is b comma b here. And the theorem here says that the eigenvalues of this matrix are the same as the eigenvalues of this transformation t. The eigenvalues of the transformation satisfy this equation, and the eigenvalues of the matrix would satisfy this equation with a replaced by m. And the eigenvectors of this matrix correspond to eigenvectors for t. Now we have to be careful. The eigenvalues of the matrix will be complex numbers. The eigenvalues of t will be the same complex numbers. The eigenvectors of m will be vectors in Cn. The eigenvectors of t will be vectors in V. So the eigenvalues are identical. The eigenvectors are in different vector spaces. So we've got to use this transformation to get from the eigenvectors of m back up to the eigenvectors of t. And we'll see how that works when we do an example. Speaking of which, here's our first example in this section. We'll find a basis D for P2 composed of eigenvectors of the linear transformation T that maps from P2 to P2. And then we want to find the matrix representation for T relative to that basis. So we want to do two things. We want to find a basis, and we'll call it D, for P2. So a linearly independent spanning set for P2 composed of eigenvectors of the linear transformation here. And then we want to find the matrix representation of T relative to that basis, D. Well, we've seen eigenvector bases before when we learned about diagonalizing matrices. One of the main theorems that we saw there said that there exists an eigenvector basis of Cn composed of eigenvectors of A if A is diagonalizable. That suggests that something about diagonalizability may come into play here. Okay, here's the linear transformation T of an arbitrary polynomial in P2 written as a plus bx plus cx squared is a plus b times x plus a plus c times x squared. So here's a second degree polynomial, here's a second degree polynomial, T maps from P2 to P2. Well, the first thing we need to do in order to find this basis is to find the eigenvectors of the linear transformation. The theorem we just saw says that the eigenvalues of this matrix for T will be the same as the eigenvalues for T. Once we have the eigenvalues for T, we can get the eigenvectors for T. How do we do that? We need a basis B. And notice it just says here in the theorem that B is a basis. It doesn't say that it has to be a particular basis. So we can choose any basis that we want for V. Well, not surprisingly, we will choose the standard basis for V, which is P2 in this case, because it's easy to work with in the sense that we can just observe coordinate vectors relative to this basis. The first thing we need to do is find the matrix for T relative to B and B, or simply the matrix for T relative to B. We need to compute the images of these basis vectors relative to the basis itself. So T of 1, well, 1 I could write as 1 plus 0x plus 0x squared. So if I compare that up here, A would be a 1, B is a 0, C is a 0. So I've got 1 plus 1, 1 plus 0, 1 plus 0 here. So I get 2 plus 1x plus 1x squared, or 2 plus x squared. So that's the image of my first basis vector. Similarly, I can write x as 0 plus 1x plus 0x squared. So I get a plus b, a plus c, which simplifies to x. And x squared I can write as 0 plus 0x plus 1x squared. So a is 0, b is 0, c is 1. Plug those numbers in, and I get just x squared. It's just a coincidence that t of x is equal to x and t of x squared is equal to x squared. That wouldn't be true for any polynomial in P2. For example, t of 1 is 2 plus x squared, which is certainly not equal to 1. Now I want the coordinate vectors of each of these polynomials relative to this basis b. 2 plus 1x plus 1x squared gives me the coordinate vector 2, 1, 1. 0 plus 1x plus 0x squared gives me 0, 1, 0. And then x squared, my coordinate vector will be 0, 0, 1. So these are my coordinate vectors. I put them in a matrix, and there's the matrix for t relative to b, which we have here. Now I find the eigenvalues and eigenvectors of this matrix. Well, we could go through all the steps. We could take the determinant of the matrix minus ix, set it equal to 0, evaluate the determinant, and get our characteristic polynomial set equal to 0, and find the eigenvalues. Or we could use the theorem that since this is a lower triangular matrix, the eigenvalues are just the entries on the main diagonal, and the multiplicity is the number of times they appear on the diagonal. So my eigenvalues are 2 and 1 has an algebraic multiplicity of 2, and we can see that here. By the theorem that we just saw, these are also the eigenvalues of t with the same corresponding multiplicities. Now I want to find the eigenvectors of m, or more accurately, the eigenspaces corresponding to each eigenvalue. So we'll start with the eigenvalue of 2. And of course, we solve the equation m minus lambda I times x equals 0. Here's m, where we essentially just subtract lambda, in this case 2. So we're going to subtract 2 from each of the main diagonals to get this matrix, row reduce it, write the corresponding system of equations, and then we get our eigenspace for 2 to be the span of the set containing this vector 1, 1, 1. And then we can see that the geometric multiplicity of the eigenvalue 2 is 1 because there's one vector inside the spanning set. For the next eigenvalue of 1, we do similar calculations, subtract a 1 from each of the main diagonals, row reduce it, write down the corresponding system of equations, and we find that the eigenspace for 1 is the span of the set containing these two vectors, and so the geometric multiplicity for 1 is 2. So we've found the eigenvectors of the matrix for t. Now we need to find the eigenvectors for t itself by using the inverse transformation from C3 back to P2. The first eigenvector we found was 1, 1, 1, and so we use the inverse transformation. In other words, these are the coefficients of the basis vectors, 1, x, and x squared, that will give me a vector in P2. And in particular, in this case, I'm going to get 1 plus x squared. With these coefficients, I'll get x. With these coefficients, I'll get x squared. So these three are my basis vectors for P2, and they are also the eigenvectors of t that form this basis. So here's the basis. Now, how do we know that this is a basis? It's got to be a linearly independent set that spans P2. Well, because of the isomorphism from P2 to C3 that we just worked with here, these are the coordinate vectors in C3, these are the basis vectors in P2, we can decide if these three vectors form a linearly independent spanning set in C3, and if they do, by the isomorphism, these three vectors form a linearly independent spanning set and therefore a basis for P2. Well, we just put these three vectors into a matrix, row reduce, we get the 3 by 3 identity, therefore we know that these three vectors form a basis for C3, and D is in fact a basis for P2. Okay, the next thing we're going to do is find the matrix for t relative to this new basis, D. Very similar to what we did when we were finding the matrix for t relative to B. It's just that now we're using a different basis, D, instead of B as before. Well, here are my three basis vectors. I've got to start by getting the images of these three basis vectors under T. Well, we actually did these before. Since these were also basis vectors in B, we saw that t of x was x and t of x squared was x squared. But here's the work repeated again just for reference. What about t of 1 plus x squared? Well, a would be 1, b is a 1, c is a 1, so a plus b, a plus c gives me 2 plus 2x plus 2x squared. So this is the image of this vector under T. Next, I want to get the coordinates of each of these three vectors relative to the new basis D. Well, let's start with x. I want to write x as a linear combination of the three basis vectors, x, x squared, and 1 plus x squared. So it'll be c1 times x plus c2 times x squared plus c3 times 1 plus x squared. Normally we'd have to solve a system of equations to figure this out, but if I just pause for a moment, I can see that there's an x here on the left side and a c1x on the right side, and then these terms I don't really even need. If I just let c1 be 1, x is equal to x, plus let c2 and c3 be 0, I'm going to get plus nothing. So c1 equals 1, c2 equals 0, c3 equals 0 would solve this equation. So if I plug those in here, I can see that x is indeed just equal to x. So the equation is solved, and therefore 1, 1, 0 are the entries in the coordinate vector of x relative to the basis d. All right, we're going to do the same thing to get the coordinate vector of x squared relative to d. And if I write out this equation, x squared is a linear combination of my basis vectors, well, here's an x squared term. So now I'll let c1 be 0 and c3 be 0. These go away, and c2 is 1, so that x squared is x squared. There's my coordinates, and here's my coordinate vector. We do the same thing to get the coordinate vector of 2 plus 2x squared relative to d. We write down the vector, and we write it as a linear combination of the basis vectors. This one may be a little bit harder to observe, but notice if I let c3 be 2, I get 2 plus 2x squared, which is what I've got on the left side, so I don't need these two terms. So let c1 and c2 be 0, let c3 be a 2, and the equation is satisfied, as we can see here. So here's my coordinate vector of this polynomial relative to d. And we take these three coordinate vectors, put them into a matrix, and here is our matrix, the matrix for t relative to d. And notice this is a diagonal matrix. Earlier, we talked about how eigenvector bases are associated with diagonalizing a matrix, and here indeed is a diagonal matrix. In particular, we have this relationship between the matrix for t relative to b and the matrix for t relative to d. These matrices are similar. And if I were to diagonalize this matrix, if it's diagonalizable, this matrix would be a diagonal matrix. Since we found it to be a diagonal matrix, we know that this matrix is diagonalizable. And if we go back and look, you can see that the algebraic multiplicities of each of the eigenvalues of this matrix are equal to the corresponding geometric multiplicities, so we know that, in fact, this matrix is diagonalizable. If we had known that in advance, we could have taken a shortcut and just diagonalized this matrix. And in fact, we weren't asked to figure out these change of coordinates matrices. We were only asked for this matrix, so we could have just written it down using the eigenvalues for t. Here they are, as you may recall, 1 and 2. Okay, let's do one more example. We're going to find a basis d for p2 that yields a diagonal matrix representation of the linear transformation t from p2 to p2 given by this function rule. Now this example is very similar to the one we just did, except that instead of being asked to find a basis d for p2 composed of the eigenvectors of t, we're asked to find a basis that yields, meaning the matrix representation for t relative to this basis is a diagonal matrix. That's what diagonal matrix representation here means. Well, based on the previous example, we know that the eigenvector basis will yield a diagonal matrix representation. So this is just another way to say essentially the same thing. We're looking for the same thing in this example as we were before. We want to find the eigenvalues and eigenvectors of t, and then the matrix for t relative to the eigenvector basis, d for t, and that automatically is going to give us a diagonal matrix representation for t. In other words, the matrix for t relative to d will be diagonal. So we're going to repeat the same steps that we did before. I've written them out here in a little algorithm just for easy reference. First, we're going to choose an easy basis, b for p2, like the standard basis for p2. We're going to find the matrix for t relative to b. We'll find the eigenvalues of that matrix. We'll find the eigenvectors of that matrix. We'll use the inverse coordinate transformation to find the eigenvectors of t. And then we'll construct a basis d from the eigenvectors of t. And we would be done. We were just asked to find the basis. We weren't asked to find the diagonal matrix, but we can check to see that this matrix is in fact diagonal, just to confirm that we did the work correctly. Okay, step 1, very easy, just choose the standard basis for p2. Step 2, find the images of the basis vectors under t. So we want t of 1, t of x squared. Here's t again for reference. T of 1 plus 0x squared is 1 minus 3 times 0 plus 3 times 0. A minus 3b plus 3c plus 3a minus 5b plus 3c times x plus 6a minus 6b plus 4c times x squared, which simplifies to 1 plus 3x plus 6x squared. A shortcut for doing all this is just to think in your head A is 1 and B and C are both 0. So just look up here, replace A with 1 and ignore B and C. So I'm going to get 1 plus nothing plus 3 plus nothing x plus 6 plus nothing x squared. 1 plus 3x plus 6x squared. Now we can do the same thing down here, except A is 0, B is 1, C is 0. So I come back up here, I'm going to ignore A and C and just take the B terms. So I'll get minus 3 times 1 plus minus 5x, or just minus 5x, minus 6x squared. And then for t of x squared, c is 1, a and b are 0, so the a and b terms here just go away, so I'll get 3 plus 3x plus 4x squared. So I found the images of the basis vectors. And we can figure out the coordinate vectors by observation. The coordinate vector for this basis vector is going to be 1, 3, 6. Since I'm using the standard basis, I can just read the entries of the coordinate vector right off the polynomial. The coordinate vector for this one will be minus 3, minus 5, minus 6. This one will be 3, 3, 4. Here they are. Put those into a matrix, and there is the matrix for t relative to b. Steps 3 and 4 I'm going to do together here. We're going to find the eigenvalues and the eigenvectors of this matrix. Lucky for us, in the notes on eigenvalues and eigenvectors, we saw this matrix as an example, and we found the eigenvalues and eigenspaces for this matrix, which I've summarized here for reference. If we hadn't already done that, then we would simply go through that process, just like in the previous example. We'd find we got two eigenvalues, 4 and negative 2. The eigenspace for 4 is this one. The eigenspace for negative 2 is this one. We also found the algebraic multiplicity for 4 was 1. The algebraic multiplicity for negative 2 was 2. And we can see here from the eigenspaces, the geometric multiplicity for 4 is 1, and the geometric multiplicity for negative 2 is 2. Because these are equal and these are equal, we know that this matrix M is diagonalizable. Okay, step 5, find the eigenvectors of t using the inverse transformation. So I'm going to multiply the basis vectors by these coefficients. 1 times 1 plus 1 times x plus 2x squared to give me this vector. 1 times 1 times x, 0 times x squared to give me this one. Minus 1 times 1, 0x, 1x squared to give me this one. So these are the corresponding eigenvectors of t in P2. Then step 6, I just put those polynomials into a set, call it B, and there's my eigenvector basis for P2. Now I know this is a basis because I know these form a basis. How do I know that? Because these are the eigenvectors of a diagonalizable matrix. And we have a theorem from that chapter that tells us that these will form a basis. So since these form a basis, this is a basis. We could confirm that by putting these into a matrix and row reducing. We would see that the matrix would row reduce the identity, meaning that these three form a linearly independent spanning set for C3, and therefore this is a linearly independent spanning set for P2. Okay, strictly speaking, we could be done here. This is the answer to the question, but we'll do step 7 and confirm that this basis will indeed yield a diagonal matrix representation for t. So how do we do that? Well, we're going to find the matrix for t relative to this new basis d. So as usual, we're going to get the images of each of these basis vectors under t. Here's the function rule again, just for reference. And now I've got this basis vector, 1 plus x plus 2x squared from up here. A is 1, b is 1, c is 2. So I plug 1 in for a 1 in for b, and a 2 in for c into each term up here, which we can see here, and simplify, and I get 4 plus 4x plus 8x squared. Then I take the next basis vector, 1 plus x, get the image of that one. Well, a is going to be 1, b is 1, c is 0 because there's no x squared term. So I plug in a 1 for a and b and a 0 for c, and all the terms simplify, and I get minus 2x. So there's the image under t of 1 plus x. For minus 1 plus x, a is minus 1, b is now 0, there's no x term, c is 1. So I plug in a minus 1 for a 0 for b, a 1 for c, into all the terms here. I get this, I simplify, and I get 2 minus 2x squared. So this is the image under t of minus 1 plus x squared. Then I need to get the coordinate vectors of each of those polynomials relative to d. We saw that the image of this polynomial was 4 plus 4x plus 8x squared. So I need to write that as a linear combination of the basis vectors in d. 1 plus x plus 2x squared, 1 plus x, and minus 1 plus x squared. And again, we get lucky because if we notice that this polynomial is just 4 times this one, I can just let c1 be a 4 and c2 and c3 be 0. I don't need these two terms. Just multiply this polynomial by 4 and I get this one. So 4, 0, 0 is the coordinate vector of this polynomial relative to d. And similarly, for minus 2x, if I observe that that's just minus 2 times 1 plus x, I could let c2 be minus 2, c1 and c3 I don't need, so they can be 0, and 0 minus 2, 0 is the coordinate vector for minus 2 minus x relative to d. Now, what if you didn't notice those things? That's totally fine. You could just write a system of 3 equations and 3 variables and solve it like you usually would, and you would get this result. Same thing here. Lastly, for 2 minus 2x squared, I want to set that equal to a linear combination of the basis vectors. And again, if I notice that 2 minus 2x squared is just minus 2 times this polynomial, c3 can be a minus 2, c1 and c2 are 0, and here's the coordinate vector for this polynomial relative to d, and I put those into a matrix, and what do you know? Here's the matrix for t relative to d, which by definition is just the 3 coordinate vectors that we found in a matrix, and I get a diagonal matrix. All right, that finishes this video on matrix representations. We defined the matrix representation of a linear transformation, as well as the eigenvalues and eigenvectors of a linear transformation. Then we did some examples where we found the matrix representation of a linear transformation, and then found a diagonal matrix representation of a linear transformation.